Hey YouTube, and welcome to the 6th episode of Operating System Development Series provided by the Iknow channel. In this episode, we're going to be mainly focusing on interrupts. This is going to be the part 1 of interrupts, so welcome again, and let's get started. Hi guys, and welcome again. So as I said before, this episode is going to be about the IDT, or the interrupt descriptor table. And since this topic might take some time, I'm going to be split it into multiple parts. So welcome to part 1 of interrupt descriptor table of the operating system development series provided by the Iknow channel. Welcome again. So first of all, let's start with the theory. So an interrupt is a signal sent to the processor from the hardware, like keyboard or mouse or clock or disk, or from the processor itself in a form of an exception. That signal tells the processor to stop what it is currently doing and do something else more important. And once done, the processor goes back to where it left off last time to continue what it was doing. We call it interrupt because it literally interrupts the processor from execution. So if someone asks you a question right now while you're watching this video, you would normally stop the video, answer his question, resume the video, and then continue where you left off. That person has actually interrupted you by asking you while you are doing something else, and you have handled that interrupt by answering him. The same thing goes for the processor. So if you have watched the 3rd episode, where we have focused on the keyboard, and take a look at the code behind it, you might notice that to get input from the keyboard, the processor keeps looping and waiting for a certain key to be pressed to return from another function. At that moment, the CPU really doesn't care if anything else happens. Whether it's a mouse click, a clock tick, an exception, or even a supernova, he doesn't care at all, or in fact he doesn't know at all. And that's simply because nobody told him anything. And that is what interrupt signals are there for, tells the CPU about external events. And to make the picture more clear for you, if you have ever programmed in different programming languages like C#, Visual Basic, Java, and JavaScript, you might already know the meaning of an event and event handlers. It is almost the same theory here. So, in order to take advantage of interrupts, we need first to tell the processor about processes first. We do that by creating an array of 256 elements. Each contains all the interrupt information for that specific interrupt. It doesn't matter where we create that array, or vector, if you might say. The only thing that the computer needs to know is where it exists in the memory. So after defining it, we tell the processor where it exists. And we need to tell the computer what is its size in memory. We do that by the LIDT assembly instruction, which stands for Lloyd Interrupt Descriptor Table. And by the way, the interrupt descriptor table, or the IDT, is actually the array that we have talked about earlier. And that's all for the processor in order to be able to access the content of the array. So as I said, we create the array, we defined each element of the array, we save the address of the first element of that array and the size of that array in another object, and then we send that object to the CPU by calling the Lloyd Interrupt Descriptor Table assembly instruction. And that's it. Of course, we're not totally done here, because we're gonna be needing to define the interrupt requests and routines and other stuff like that. but that's going to be left for the next parts of this videos, which means that at the end of this video, you're not gonna be noticing the change in the operating system. So let's get started with coding this part. So we go back to the project we left off earlier, and as you can see here, inside the include folder here, we have defined another file called utilities, so util.c and util.h, and we've also created a new file, idt.h and idt.c. So let's first start with the utilities first. So we go to utilities.h, and as you can see here, we've created a few basics functions here. The first is called memory copy, and the second is called memory set, and the third is called int to ASCII or int to string, or that's the convention. It's just like the I2A function in the C libraries. So the memory copy actually takes the address of the source, the address of the destination, and the number of bytes that we want to copy, and starts copying all the bytes from the source to the destination. That's it. And the memory set is going to be setting the value, setting a specific value to a destination. So we set the address of the destination, we set the value that we want to set, and we set the length, how many times we want to set that value inside the destination. So if, for example, here we've got 10, we're going to be, and the value is 20, we're going to be setting the value 10 times inside the destination. The first place, the second place, the third place, all of them up to the place number 10, all of them get the value of 20. And finally, the int to ASCII here takes the number and the string pointer or the string array, and it basically converts an integer to a string. So for example, if we have 1, 2, 3, 4, 5, it becomes 1, 2, 3, 4, 5. That's it. Okay. Now if we move to the utilities.c here, you can see that here we've got the definition of the declared functions: memory copy, memory set, and int to ASCII. So the memory copy here, we've got an integer variable called I, is going to be the counter, and we're going to be looping n bytes time, and each time we put to the the source of I, the value inside the source of I, we put it inside the destination of I. So this is the notation of the asterisk is the notation of the pointers. I wanted to use this notation here to make a little bit of changes so that you can understand both of them. But if you're not okay, you can also use this notation here. So the source of I, the destination of I is going to take the source of I. So both of these notations are equivalent. And here we've got the definition of the memory set. So the same thing goes here. We are creating an assigned integer of 8-bit variable, which is a pointer, and then we loop length times, and each time we keep looping, and we put inside the temp the value that we have got here, and until the length is different to 0, and each time we do that we decrease the length by 1. So that's a different way of looping, but it's actually means the same thing. And finally here we've got the int to ASCII, which we take the integer and the final string. We create an integer variable called I and an integer variable called sign, and if sign is equals to n, so the first thing we're going to be doing is we're going to be putting the n here inside the sign, so we're creating a local instance of that value so that we do not make changes on it. And we're comparing that n. If it is less than 0, then n is going to take minus n. So if the number is negative, we're going to be taking just the opposite of it. So if it is minus 5, we're going to be considering it as 5. And here the first thing is we're going to be putting the counter I to 0, and we're going to be do while loop. So we're going to be the string of I plus plus. So the first one is going to be the string of 0 is going to be taken our number here, the modulus of our number by 10, and then we added the character 0. So if it is, for example, 69, we're going to be taking the modulus of 10, which is going to be actually 5, and then we add to that 5 the character 0, which is actually 48, and we get here 53, which is the character of 5. So if we take a look at the ASCII code, check the character 5, we're gonna find it that it equals 53 integer. And of course, after calculating that character, we put it inside the string until the modulus is less than 0. So we'll keep doing this as long as the modulus of until the n divided by 10 is bigger than 0. So if it becomes less than 0, then we're going to be stopping the execution there and we move to the next instruction. And then finally, if the sign is less than 0, we're going to be adding a minus there. If it is bigger than 0, we're not going to be doing anything. And at the very last, we're going to be adding the null character so that the string ends with a null character. That's essential, so that when we use that string in other functions later, like string length and other functions that needs the null and terminated character, we're not going to be ending with a bug or something like that. So, okay, now let's move to the important part here, because these functions here are off the topics actually. So if you go to the idt.h here, as you can see here, we are the include this file here depends on the type.h. For that reason, we have here include types.h, and here we're going to be defining the kernel _cs to 0x08, which is the segment selector. Actually, I'm going to be explaining this later, but for instance, you have to make this value stick to this. This is going to be stick to this value for the entire tutorial. So as you can see here, we are defining two structs, struct1 and struct2, and then after that we use the struct1 to create an array of 256 elements, and we use the second struct to create a variable from it, and here we define a couple of functions. So if we go back to the first struct here, so the first struct is going to be defining each element of the interrupt descriptor table. So as we said before, the interrupt descriptor table is an array which has 256 elements. So to define each element, we have to put values inside it. So the first byte means something, the second byte means something, the third byte means something. So instead of talking to those bytes directly with numbers, it is a better practice to create a struct and organize them so that we can easily access them later without having to take a lower abstraction layer for our code. I mean, the goal here is to define this crap, literally, this craps once, and then we do not look at it again anymore. So the first The first property we're defining here is of type inside integer of 16-bit, which is going to be the low offset of the struct element. The low offset means the I'm gonna tell you what this low offset is, but first let's go back and let's go to the types.h here. There's something I forgot to tell you. Remember to define these two functions here. So this is going to be called the low 16 and this is going to be the high 16. These two functions actually takes a 32-bit integer and divide it. So for the low 16 is going to take the right 16 bits of the integer, or the low 16 bits, and for the second one is going to be taking the high 16 bits of the integer, or the left side 16 bits. So this is going to be taking the right side 16 bits and this is going to be taking the left side 16 bits. That's what these functions does. So if we go back to the idt.h, this is going to be taking the low offset that is going to be generated from this function, and this is going to be taking the high offset, which is going to be generated from this function. And as you can see, this is defined at the first place of the struct, and this is defined at the last space of the struct. And remember that the order matters. And this is going to be the selector. Actually, I'm going to be explaining these later, since we do not need to understand them for this for the purpose of this video. But I'm defining them since they're essential in later buildings. Here we've got the always 0. This stands for the ring. The ring tells the processor whether a certain interrupts can be executed from the kernel only, or from the user space, or from what is in between. And finally, after building this struct, as you can see here, we've got 16 bits, 16 bits, 8-bit, 8-bit, 16 bits. So the sum of these is equals to 64 bits. And the number of bits actually matter. We want it to be just like that. We do not want the compiler to add extra space or extra code or extra thinking that is going to be to stabilize our code or stuff like that. For that reason, we add this attribute here, which tells the compiler, okay, compiler, I want you to generate this space areas as I tell you. Do not add anything by yourself. And finally, the struct name is going to be idt_gate_type. So after creating this struct, we are creating an array of 256 element from it. So this struct is going to be existing 256 times, and then we are going to be defining each element of it. So each element takes a low offset, a selector, an always 0. This is going to be taken always 0, flags, high offset, and stuff like that. And here we have the second struct definition here. So this struct is called IDT, interrupt descriptor table _register_type. As I mentioned before, it needs to be compiled as it is, no extra garbage added by the compiler, and the total size of it is going to be 48 bits. So the first 16 bits are going to be the limit, and the seconds are going to be the base. So the base actually is going to take the address of the IDT array here. So we are defining a couple of structs here inside an array. We need to know the first address of the first element. We need to know the address of the first element of the array, so that we can tell the processor later where to find this array, this interrupt descriptor table. So we store that array inside the base here, and we store the size of that array inside the limit here. So that's the job of this interrupt register type here, and that's why we are actually creating only one object and not an entire array, because this variable here, this object, needs to be existed once. It's going to take the first address of this array, and it's going to take the size, the total size of bits of this array. And finally here we have the set IDT gate. This function is going to be actually called multiple times. So each time we want to describe an element inside that array, we call this function. We give it the number of element we want to define, and we give it the handler, which is an inside integer of 32-bit, which is going to help us define the content here of this struct. And finally set IDT. So we call the set IDT gate multiple times, and after defining all of the elements inside the array, we call the set IDT to take that array, that final array, to the processor. So let's take a look at a closer look at the IDT.c. So this is it, and inside it, as you can see, we've got the definition of those two functions, the set IDT gate and the set IDT. And as you can see here, the set IDT gate, we are taking the element that we want to define from the array, and we're taking the handler that will help us know how to define it. So the IDT of n of that element that we're going to be taken from the parameter there, dot low offset, is going to take the low 16-bit of the handler. So this IDT object here is what we defined here, that's the array. And the dot low offset is the property of the struct IDT gate, since that this this array is of type IDT gate type. So it has low offset property, selector property, always property, flag properties, and high offset property. So the low offset property, we said, is going to take the the left side 16 bits of this 32-bit inside integer, and the selector is going to be taking the kernel segment selector that we have defined above here, and the always 0 is going to be taken 0, as it's called. Always 0 is going to be 0. It's the ring level of execution, so it's ring 0. And the flag is going to be OX8E, and the high offset is going to be high underscore 16 of the handler. So here we're taking the left 16 bits of the parameter that we took there. So what really matter about this handler is the low 16 bits and the high 16 bits here. And finally, after calling this function multiple times, each of which defining an element inside the array, after all of this happens, we call this set IDT only once. This set IDT is going to be taken the resulting array and give it to the processor in order to start looking at it and do what it wants to do with it. So the ITT_reg object that we have created here from the second struct, the base property is going to be taking the address of the array. So this mark here means the address of that variable. So this array object, we take the address of it, of course we cast it to inside integer of 32, and then we give it to the base property of the IDT register object. And of course the second one, which is called IDT_reg.limit, which we said before is going to take the size of the array. It's going to take the IDT gate t, the size of it. The IDT gate t, we said that it is the struct, the first struct, which is going to be defining each element. So we take the size of each element, We subtract 1 from it, since the size, as we said before, it's 64, so subtract 1 from it, it becomes 63, and plus the first element, which is indexed by 0, it becomes 64, so the size is correct. And then we multiply it by the IDT entries, which is the number of elements inside that array, which is actually 256. So we get finally the number of bits of the entire array. And after having these two essential informations, we call the Lloyd IDT, Lloyd interrupt descriptor table assembly instruction to take that to take this object, the IDT reg, so that the processor can handle that interrupt descriptor table. So this video is, as we said, is about the interrupt descriptor table. The next one is going to be about the interrupt service routines. And if you have been watching this so far, so thank you guys for watching. And yeah, you've been watching, and that's why you're hearing me talking right now. So thank you guys for watching, and see you in the next video.